Welcome back to this course on advanced manufacturing and process modeling. So, today we will start with a new module which speaks about process modeling of casting processes. So, so this is basically the content, that is transport phenomena during solidification, governing equations, phase change, finite volume based, multi-phase and multi-scale model of solidification, initial boundary conditions for solving the flow physics, phase field model of solidification microstructure formation, as well as defect generation. So, an enthalpy model for convection diffusion based phase change method. So conservation of mass, which reduces to continuity equation. So here it is written for two dimensional form, that is applicable to the z and y direction. So the velocity corresponding to z direction is w, and velocity corresponding to y direction is v. So then the conservation of mass reduces to the continuity equation, that is del v del y plus del w del z is equal to 0. And then the conservation of momentum, the standard form is del del t rho v, that is the velocity, plus divergence rho v v, velocity again, is equal to divergence mu grad v minus del p del y, that is p is the pressure over here, and s plus sy is the source term. And then for the this is for the y direction momentum, and for the z direction momentum can be expressed as del del t rho w plus divergence rho v w, that is divergence rho y velocity into z velocity is equal to divergence mu grad w minus del p del z, pressure variation in the z direction, plus sz plus sb. So where p is the pressure, rho is the density, mu is the liquid viscosity, dynamic viscosity actually, u is equal to the velocity, which is having two components in y direction as well as z direction, and sy, sz and sb are source terms which will be defined later on. So the heat equation after momentum, so this is the third conservation equation that need to be satisfied by a fluid flow heat transfer problem, which can be expressed as del del t rho h plus divergence rho u h is equal to divergence alpha grad h, h is the heat transfer coefficient, convective heat transfer coefficient, minus sh, which is equated to 0. So where alpha is equal to k by c, alpha is the thermal diffusivity, k is the thermal conductivity, and c is the heat capacity, and sh is a phase related source term that will again can be discussed later. So, so on recognizing that latent heat is associated with the liquid fraction in the mushy zone, a general form for Ft, where Ft is nothing other than is equal to delta H. So here as we know, the enthalpy of a material capital H is equal to small h plus delta H. So where small h is equal to heat capacity multiplied by the temperature. So it is basically the sensible heat, and delta H is basically the latent heat here. So delta H is the latent heat, which is expressed over here as a function of temperature. So delta H is equal to function of T, temperature. So then we are on recognizing that latent heat is associated with the liquid fraction. This is the general form that has been written over here. So this is the general form. So here then Ft is equal to capital L, that is the liquid fraction becomes equal to capital L when temperature of the solidifying liquid is well above the liquidus temperature in case of an alloy. So then the liquid fraction is equal to L, and then when the temperature lies in between the liquidus and solidus temperature, what is the condition over here? So where TL is greater than T but T greater than Ts, so somewhere in between. So if I draw a simple phase diagram for your ease of understanding, this is a copper nickel phase diagram, Lenz type phase diagram. So so here it is for nickel, which is increasing this side, this is copper. So then here assume that there is a particular alloy. So in that case, this is TL, this is TS. So this is a condition where temperature lying somewhere in between. So this is basically T over here, and then so the this latent heat becomes 0 when T less than Ts. That means there is no phase change involved. I mean, so that time, so I mean the so the it is totally, so the total content is solid, and in the mushy zone the liquid fraction can be obtained by deducting the solid fraction from the total volume. That means 1 minus Fs. So this is the situation. So here this is how we can do the formulation for latent heat, and then if we can apply switch off technique, so which is one of the simplest approaches for modeling velocity changes during solid liquid phase transitions, and it works by setting the velocity in the solid region to 0. So this technique relies on identifying the solid and liquid regions based on the predicted latent heat contribution to enthalpy, and when the latent heat of an element reaches a threshold, so the velocity in that element is set to 0, indicating the completion of phase change. So that means from velocity we can distinguish that the phase transformation has happened. In case it is liquid to solid transformation is happening, so the velocity in the solid phase is equated to 0. So from here it can be recognized, and then the next case, the variable viscosity technique, is a more refined method that adjusts viscosity as a function of temperature, particularly in the mushy region where phase change is occurring. So in this method the viscosity increases significantly in the mushy region. That is because increasing solid content within the solidifying melt, which is responsible for enhancement in viscosity because of the pseudoplastic nature of the at mushy state of the liquid melt. So effectively limiting the viscous velocity in the solid region. So as and when solid formation is increasing, the velocity of the mush decreases because of the increasing viscosity of the mush, and as the phase change progresses, the viscosity increases. So which can be understood that when the solid fraction keep on increasing, the viscosity keep on increasing, viscosity of the mush keep on increasing, and once phase change is complete, then the latent heat exchange delta H is equal to 0. So this is the basic concept for phase change, liquid to solid phase change basically. And now the procedure for numerical modeling of the solidification process. So governing equations, we can so we use single domain mass, momentum and energy conservation equations for modeling the solidification process, and we can implement the Darcy drag source term in the momentum conservation equation to handle the fluid flow in the mushy region, whereas enthalpy porosity technique can be applied to update the liquid fraction for each computational cell when there is a impending phase change happening. That means liquid to solid transformation is in place, and the model assumptions are the fluid is incompressible, laminar and Newtonian in the liquid phase, and constant physical properties for both liquid and solid phase, and Bosenskiu approximation for the density variations in the liquid due to temperature gradients that exists during solidification. So a simplest understanding of temperature gradient, like we have discussed earlier when we were discussing casting. So because solidification start from the wall, so so basically the solidifying dendrites or cellular structure, it grows opposite direction to the heat removal, and there exists a thermal gradient. So assume this is the solid liquid interface. So then for columnar growth, from interface, it is the temperature which grows in the liquid. So that is a case of positive temperature thermal gradient, positive Tg. Okay. So that is promotes the dendritic grain structure. So this is the example of thermal gradient. So the solid phase is assumed to be non-deforming and free of internal stresses. So these are the model assumptions. After that, the momentum conservation. So introduction of a source term using Karman-Kozni's equation can be done to handle the velocity jump across the solid liquid interface, and a buoyancy source term can be implemented as in line with Bosenskiu approximation for the body forces in the momentum equation. So this is the treatment of the momentum conservation, and after that the treatment that has needed to be followed in case of energy conservation. So solving the energy equation with a source term for latent heat release using the enthalpy update scheme, and updating the latent heat content of cells based on local temperature values and computing the liquid fraction accordingly. So, and then enforcing physical bounds on latent heat to prevent non-physical values during updates. So, these are the treatments that can be followed for a simple solid liquid, liquid solid phase change model. So, now we will be discussing to how the momentum equation can be derived in 3 dimensions. So, we can start from the basic Newton's second law, which states that force is equal to mass into acceleration. So, so if we are talking about x direction, then it is m into ax. So, this is the Newton's law, of Newton's second law. So, rate of change of momentum of a fluid particle equals the sum of the forces of the particle, and then rate of increase of momentum of fluid particle is equal to sum of forces on fluid particle. So, the rates of increase of x, y and z momentum per unit volume of a fluid particle are given by rho du dt, rho dv dt, that is for x direction, okay, and rho dv dt for y direction, rho dw dt. So, these are substantial derivatives. So, in the for z direction. So, we can distinguish two types of forces on fluid particles. So, number one are surface forces, which includes pressure forces, viscous forces and gravity force, and number two are body forces, which are which include centrifugal force, Coriolis force and electromagnetic force. So, so here please correct this mistake. This gravity force should be put into the body forces. So, surface forces are limited to pressure forces and viscous forces only. So, so it is common practice to highlight the contributions due to the surface forces as separate terms in the momentum equation and to include the effects of body forces as source terms. So, how we are arriving at that treatment I will be discussing next. So, so the states of stress of a fluid element is defined in terms of the pressure and the 9 viscous stress components that is shown in this figure. So, this is the viscous stress components in the x, y and z direction. So, so the usual suffix notation tau ij is applied to indicate the direction of the viscous stresses. So, the suffixes I and j indicate that the stress component tau ij acts in the j direction, that is on a surface normal to the I direction. So, this is how the notation is given, and that is true for all other direction. For example, if the stress component speaks about x z, then it is basically the stress in the z plane, z direction in a plane which is normal to the normal to x direction. So, this is how for the notations are given in this image, which is shown over here for this cubic fluid element, which is shown over here. And then so then the forces in the x direction on a fluid particle. So this will be, again it can be clear from this. There must be a okay. So, this cube, it may be difficult to understand. So, maybe I will draw so that it can be easy to understand. So, if I draw a simple cube, okay. So, here you so here it is, the axis is like this. So, this is in the x direction, this is in the z direction, and this is in the y direction, like the previous image. Okay. So, here so then it is the the pair of faces. So, then it is so it is the east and west. So, this is the east face and this is the west face and this is the north face, this is the south face. So, this is how the fluid element is shown over here. So, here so then on the pair of faces E and W, so when we are considering only the east and west faces of this fluid elements, and then we can write P minus del P del x by 2 minus tau xx minus del tau xx by del x into delta x by 2 into del y del z plus P plus del P del x. So, it will be clear for the pressure. So, if you can write in this way, so it is going towards the positive x direction. So, then P minus del P del x delta x by 2, and then it is going towards the negative x direction. So, then it is basically P plus del P del x delta x by 2. So, here one thing is there. So, generally the notation for all other like stresses like tau shear stresses. So, the notation considered in this derivation as the flux which is going towards positive x coordinate is considered as positive, and then the which is going towards negative y negative x it is considered as negative. Same treatment is applied for y and z direction as well. However, in case of pressure the treatment is little different. So, that is why the minus sign is there, because here the minus sign is given to accommodate for the, because towards the positive x direction it is the pressure force applied over the fluid element is compressive in nature, and whereas so that is why it is the negative sign is coming here. That is why it is P minus del P del x into delta x by 2, whereas in this case the in the east face the pressure force applied, that is P plus del P del x into delta x by 2. So, here the positive sign comes because here it is basically a tensile in nature. So, that is why the positive sign is coming. So, here if we balance the forces in the x direction over the fluid particle, then we can write P minus del P del x by 2 minus tau x x minus del tau x x by del x into delta x by 2 del y del z plus P plus del P del x minus delta x by 2 minus tau x x. So, plus del tau del x x x by del x into delta x by 2 into del y del z. So, it becomes, if you rearrange the terms, then it comes as minus del P del x into delta x delta y delta z, because other terms gets cancelled up. So, you can understand from here. So, if I write it from here, so then P minus del P del x delta x by 2 into del y del z, and so here also P into del y del z, okay, and then so minus this one we have written, and then minus tau x x del y del z plus del tau x x by del x delta x by 2 del y del z, and then plus P del y del z, okay, plus del P del x by into delta x delta y delta z by 2. Okay. So, these two terms gets cancelled readily, minus tau x x del y del z minus, so del tau x x delta x del x del y del z by 2. Okay. So, here we can see this term gets cancelled with this term. So, then what is the resultant expression? So, then we are getting as so here we are getting minus del P del x plus del tau del. So, here it is so the net force in x direction is coming as minus del tau x y minus del tau x y by del y into del y by 2, when we are considering the north and south faces. So, so it is coming as minus del tau x y minus del tau x y by del y into delta y by 2 into del x del z plus del tau x plus tau x y plus del tau x y by del y into delta y by 2 into del x del z, which becomes equal to. So, here you can see this term gets cancelled with this term, and then so this becomes equal. So, this becomes additive to this term, and then so then 2 it comes at the ahead, and then 2 and this 2 gets cancelled, and then finally it comes as del tau x y by del y into del x del del x del y del z. So, finally, the net force in the x direction on faces top and bottom. So, so it is about top and bottom faces is given by so it is so here if you just do the correction, so here it is top and bottom, and then here it is north and south. So this one if you consider as north, this face we are talking about, then this face becomes south. So this is how you can treat it, and then so for top and bottom face it can be given by minus tau zx minus del tau zx by del z into delta z by 2 into del x del y plus tau zx plus del tau zx by del z into delta z by 2 into del x del y. So then again you can see here that this term tau zx gets cancelled with this one, and then this becomes additive. So then 2 del tau zx by del z into del x del y del z. So here there is a 2 at the denominator. So then 2 gets cancelled. So then the resultant expression becomes del tau zx by del z into del x del y del z. So so here you can see that so there was a mistake which was happening. So here there will be a minus sign coming, and that is why the treatment was so and then here there will be a plus sign over there. So that is that is why it is coming. If you then rearrange the terms, then it can come like this. Okay. So that is that was the error earlier. So that is corrected now. So please consider this as plus sign, and here there has to be a minus sign. Okay. So this was the typographical error. So please correct it, and then so the total force per unit volume on the fluid due to these surface stresses is equal to the sum of the above equations. So divided by the volume delta x, delta y and delta z. So then from this expression we get, so there are 3 terms we are getting, that is the pressure term minus del p del x delta x del y del z, and then there is the shear force, shear stress in the x direction for the north and south faces, and shear stress in the x direction for the top and bottom faces. So then we if you do additive, if you do the addition and then divide it by the volume delta x delta y delta z, so then the resultant expression becomes like this. So del minus p, so minus p coming from here, plus tau xx by delta x, and then plus del tau xy del y plus del tau zx by del z. Okay. So so here there has to be another correction which will be needed here. So this term was missing here. So it should be del tau xx by del x delta x delta y delta z. Okay. So then if you correct it, so then the final expression becomes like this, that is del minus p plus tau xx by delta x plus del tau xy by del y plus del tau zx by del z. So without considering the body forces in further detail, their overall effect can be included by defining a source Smx of x momentum per unit volume per unit time. So the x momentum of the momentum equation is found by setting the rate of change of x momentum of the fluid particle equal to the total force in the x direction on the element due to surface stresses plus the rate of increase of x momentum due to sources. So then the momentum equation for each component can become, so if you recall that initially we have told that the rate of increase of x, y and z momentum per unit volume of a fluid particle were depicted as rho du dt, rho dv dt, rho dw dt. So these are where d dt is the substantial derivative. So then this is the rate of increase of momentum of fluid particle. It has to be equated with the sum of forces on the fluid particle. So now we have identified, and this is the sum of forces. So then let us equate it with the rate of increase of momentum for the fluid particle. So if we equate it, then for individual components of the momentum equation we can get. So for x component we can equate it with rho du dt, which becomes equal to del minus p plus tau xx by del x plus del tau xy by del y plus del tau zx by del z plus the source term in the x direction, which constitutes the body forces, that means gravity force and other Coriolis force etc., what we have discussed before. And then for the y component, again it is the similar treatment can be done to derive. So, that is why it is not shown here. So, only the derivation for the x component is shown here. So, but the expression will be pretty similar with the x component, and it will be of the form rho dv dt is equal to del tau xy by del x plus del minus p plus tau yy plus by del y plus del tau zy by del z plus smy, that is the source terms in the y direction. And then for the z component, again for the similar treatment. So, rho dw dt is equal to del tau xz by del x plus del tau yz by del y plus del minus p plus tau zz by del z plus smz, that means the source source term for the z direction. So, the explanation as I have told earlier only, the pressure sign convention assumes a positive normal stress correspond to tension and pressure compressive normal stress. So, that is why it has a negative sign, and smx, smmy, smz represents the source terms due to body forces. So, for example, gravitational body force, that is smx, because gravity is only acting in the z direction. So, smx becomes 0, smy becomes 0, and only smz, that is becomes equated to rho minus rho g, because gravity acts towards the towards downward. So, that is why the negative sign is shown over here. And then so that is how we can come to the expression for the momentum equation, so for x, y and z direction. And now so if we are introducing the Navier-Stokes equation for a Newtonian fluid. So, we can arrive at the Navier-Stokes equation from the momentum equation. So, how we can arrive at the Navier-Stokes equation, we can see here. So, viscous stresses in fluid dynamics. So, the definition are the viscous stress components tau ij are crucial unknowns in the governing equations of fluid flow. So, modeling. So, these stresses are typically modeled as functions of the local deformation rate or strain rate. And then the deformation in fluid. So, the deformation rate composition. So, linear deformation rate, it measures elongation or distortion. Volumetric deformation rate, it measures changes in volume. And then isotropic fluids. So, most gases and many liquids are isotropic, where viscous stresses depend only on deformation rates. And anisotropic exceptions, polymer containing liquids may exhibit anisotropic stresses due to chain alignment, but such cases are beyond of this course. So, we will not be discussing that here. So, now let us focus to the linear deformation rate components. So, the components, linear deformation of a fluid element in 3D has 9 components, but in case of isotropic fluids the 6 components are independent. So, the notation denoted as Sij here, these components with a suffix system identical to the stress component. So, then Sij, so when it is Sxx, so then it is equal to del u del x, Syy is equal to del v del y, Szz is equal to del w del z. So, there are also 6 shearing linear deformation components. What are they? Sxy, which is equal to Syx is equal to half del u del y plus del v del x, Sxz is equal to Szx is equal to half del u del z plus del w del x, and Syz is equal to Zy is equal to half del v del z plus del w del y. Okay. So, then this is for the y and the z direction, and then followed by this, if we now enter into the derivation for the momentum equation. So, then derivation for the Navier-Stokes equation. So, the volumetric deformation is given here as del u del x plus del v del y plus del w del z is equal to divergence u. So, in a Newtonian fluid, the viscous stresses are proportional to the rates of deformation, the 3-dimensional form of Newton's law of viscosity, and the second viscosity, that is delta, to relate stresses to the volumetric deformation. The 9 viscous stress components, of which 6 are independent, are tau xx is equal to 2 mu del u del x plus delta divergence u, tau yy is equal to 2 mu del v del y plus delta divergence u, and then tau zz is equal to 2 mu del w del z plus delta divergence u, and then tau xy which is equal to tau yx is equal to mu del u del y plus del v del x, and tau xz which is equal to tau zx is equal to mu del u del z plus del w del x, and tau yz is equal to tau zy is equal to mu del v del z plus del w del y. So, I mean so this is known about the second viscosity delta, because its effect is small in practice. So, for gases a good working approximation can be obtained by taking the value of delta is equal to minus 2 by 3 mu. So, it should be mu, please correct it. So, liquids are incompressible. So, the mass conservation equation is divergence u is equal to 0. So, and the viscous stresses are just twice the local rate of I mean linear deformation times the dynamic viscosity. So, substitution of the above shear stresses into so below written equations yields the so called Navier-Stokes equation. So, which is given in the next slide. So, named after two 19th century great scientists who derived them independently. So, so that is how the I mean the Navier-Stokes name came. So, then here as we have written the expressions for the momentum equation in the x direction, in the we have introduced it earlier also, but for your ease of understanding it is written again. So, for x direction it is rho du dt, that is substantial derivative of u is equal to del minus p plus tau xx by del x plus del tau xy by del y plus del tau zx by del z plus smx. And for y direction it is for rho dv dt is equal to del tau xy by del x plus del minus p plus tau yy by del y plus I mean del tau zy by del z plus smy. And then for the z direction it is rho dw dt is equal to del tau xz by del x plus del tau yz by del y plus del minus p plus tau zz by del z plus smz. So, where smx, smy, smz are the source terms which are written here to consider the effect of the I mean body forces. Okay. Yeah. So, I mean so next so then Navier-Stokes equation how we are getting now. So, basically now the expressions of the I mean the relationship between the stress component and the linear deformation component as well as the volumetric deformation components. Now, we are I mean introducing it into the I mean momentum equation. So, the values for tau xx, tau yy, tau zz and tau xy, tau xz and tau yz are introduced into the equation, and then the equation takes the following form. So, the rho du dt is equal to minus del p del x plus del x 2 mu del u del x plus delta divergence u. So, because we have written over here that tau xx is equal to 2 mu del u del x plus delta divergence u. So, I mean so similarly I mean it is just kept over here 2 mu, and then similarly for plus del y tau xy. So, like we have expressed here tau xy is equal to mu del u del y plus del v del x. So, which is I mean expressed here, and similarly plus del z. So, tau zx. So, tau zx we have written like is equal to mu del u del z plus del w del x. So, that is why I mean so that is what is shown over here. So, yeah. So, tau zx is equal to I mean this is the del u del z plus del w del x. So, I mean so here that is shown given over here del u del z plus del w del x plus source term in x direction, that is for we get the Navier-Stokes equations for the x direction, and then similar treatment we get the Navier-Stokes equation for the y direction and for the z direction. So, then moving ahead we will now discuss about the energy equation, but we will discuss it in the next class. So, we are stopping here for this class, and so we will meet again. Thank you.